Hi, my name is Mike Schell, and I'm with AirTest Technologies, a Vancouver-based sensor company that specializes in a wide variety of sensor technologies for building control. This presentation today is actually going to cover two topics, which really is the use of CO2 demand control ventilation and dew point economizer control to properly and economically control fresh air ventilation in buildings. Now, to give you a bit of background, AirTest manufactures a wide variety of sensor products. They're kind of shown here. And if you want to drill down and look into some of the products, see what's going on, you can basically just go to airtest.com and go to our product page, which is accessible through the top menu of the website. And you'll basically see these illustrations allowing you to drill into whatever sensor solution you're looking for. Today, we're going to be talking then about CO2 control and dew point economizer control. And as we go through the presentation, we're going to talk about the different ventilation modes of buildings, basically what CO2 demand control ventilation is and why it works, what are some of the CO2 products that AirTest has, and then we'll go to take a look at the moisture side and talk about things that affect moisture control in buildings. We'll talk specifically about using the fresh air economizer control and some of the economizer control products we use today. And then basically we'll pull it all together. I might also note that if you don't have time to watch this all at once, you might want to consider just watching the CO2 part first and then watching the moisture part second. I'm not too sure, but I think they should both take about the same amount of time. Probably about, we'll see how we go, but it's probably about 15 to 20 minutes per topic. So here we go. And one of the reasons we're combining both of these things into one presentation is because here we have a circle that shows the different time periods where we might have cooling, heating, where the economizer might be operating, a fresh air economizer, and where, let's say, the building is neutral, where it needs no heating or cooling. This may change somewhat depending upon what climate you're in, but basically there's two operating modes of ventilation. One is that you have a period of time where you're providing the minimum design ventilation to the building or activating CO2 demand control ventilation. And then you have this other portion of the time where if you can use outside air for free cooling, you're actually using an economizer control. And it's important that we really pick the right strategies that allows maximization for economizer control when conditions are right outside and for CO2 control when the economizer control is not appropriate. So that's what we're going to talk about today. And you're going to get a lot of background on really how ventilation works in buildings. So let's get into the CO2 demand control ventilation. I guess as people were looking at indoor air quality in buildings, this is somebody's bright idea of a way to have a quiet workspace and get his work done. So I just thought it was an interesting historical picture. But speaking of history, I guess, it was a few years ago I was speaking at an ASHRAE meeting in Seattle, actually, and somebody came up to me and showed me this copy of the Mechanical Engineer's Handbook. You can see it was published in 1916, and actually over on the right-hand side here, you can see that Willis Carrier was actually one of the authors. Now, to put things in perspective, in 1916, mechanical ventilation in buildings was like science fiction. Probably a half of 1% of buildings actually had something called mechanical ventilation. Most buildings had fireplaces, I guess they had steam, and they had openable windows. And openable windows was the ventilation for buildings. Well, in this handbook, they imagined there might be some day where some crazy person, because they had mechanical ventilation, would actually design a room without openable windows. And so in this handbook, they actually said, well, how do we make sure there's enough fresh air getting to the space that doesn't have a window or doesn't have an openable window? And they really laid out here the fundamental relationship between CO2 and ventilation, saying that really that the limit, the concentration in the space should not exceed 8 to 10 parts in 10,000. That's actually 800 to 1,000 parts per million, the same basic values that we use today, but this was back in 1916. So back in 1916, they figured out that CO2 could be a good indicator of ventilation, except I don't know whether they were too certain how you measure it. It must have been some sort of chemistry kit or something where they would check it. So they didn't have monitors that could go on the wall like we do today. The other interesting thing is I wrote an article on CO2, and somebody who actually used to work for New York City actually showed me the 1929 building code, where they actually adopted the information from the 1916 Mechanical Engineer's Handbook and had it in the 1929 building code. So CO2 ventilation control, we've known about it for a long time. The issue is really it's only in the past 10 or 15 years that we've had the technology to do it effectively. And to give you some of the background behind this, the reason why we can use CO2 to control ventilation is that because there's a direct relationship between activity level in a space and the amount of, or the activity level of people and the amount of CO2 they produce. So here you can see different activity levels and the ramp of CO2 production goes up. I always find it interesting, though, how the distance between sleeping and office work really is very minor, so not much of a difference. But for the purposes of building control in office buildings, build schools, areas with primary occupancy, generally what we assume is office work, which is sort of a combination of sitting, standing, maybe walking a bit, talking, maybe a bit of sleeping. That all tells us that individuals are producing about 0.3 liters per minute of CO2. And that's true of people ranging in age from about 11 to 65, male and female, plus or minus about 20%. So what that means is that in a space, if you have a certain number of people, you double the number of people, you'll double the amount of CO2 produced. And that's really the fundamental principle behind using CO2 for ventilation control. Is in one way, it's a way to count people. It's also a dynamic measure of really the number of people in the space breathing and the amount of outside air coming in to dilute the inside air concentration. And that allows us to correlate this directly to a ventilation rate per person. And I don't know, you might have done CO2 measurements in the space before. This is actually, this red bar area here shows CO2 concentrations as they start at the beginning of the day, levels rise up, and then levels go down again at the end of the day. And this shows an important principle of CO2, how it behaves in a building, in that when people start coming in and breathing, it builds up. But then, as you can see, it starts to level off right at the very top. And that leveling off point is called the equilibrium level, where the amount of CO2 coming in from outside is equalized with the CO2 actually produced by people. Knowing what this equilibrium is, we can actually get an idea of what the ventilation rate is. And in this particular application, where levels built up to about 700, or I guess just below 700 parts per million, we can translate this into a ventilation rate of about 35 CFM per person. So this space was actually being overventilated, and we could tell it by doing this day-long measurement. So if we then look at the relationship between CO2 and ventilation rate, we can see that a certain differential between inside and outside concentrations can give us different ventilation rates. So for example, if we assume outside levels are 400, which they are about now, and we looked at, let's say, an indoor concentration of 1100, that would give us about 15 CFM per person. If concentrations were 900, that would be about 20 CFM per person. If levels built way up to 2,500, we'd be seeing about 5 CFM per person. And of course, this rating of ventilation per CFM per person is one of the issues where codes and standards generally address ventilation requirements by setting out a CFM per person ventilation rate, typically 15 or 20 CFM per person. So where do the savings from CO2 come from? Here are two occupancy graphs, one for a weekday, one for a weekend, and and the line that goes up and across the lower line just shows really what the operating period of the mechanical system is, and the bars actually show what the occupancy of the space is. We're looking at probably a typical office building. Well, the thing with CO2 is we can actually control to the actual occupancy in the space, ensuring that the CFM per person for the number of people in the space is met. The net result is the first place where we can save energy with CO2 demand control ventilation is on variable occupancy. If the space is not fully occupied, we can modulate the ventilation down so we're providing the right per person rate, but we're not providing it for the entire full occupancy of the space. Second, often spaces are actually people don't know what the setting is, or people play with the air intake setting of the building, and actually many buildings are overventilated. EPA study of about 100 commercial buildings a few years ago found that over 80% were ventilated almost twice of what the standards might require. So we can also, with CO2, control, we have a feedback mechanism to actually regulate the amount of fresh air coming in so we're not reducing or we're not overventilating the space. Finally, for some buildings that have occupied and unoccupied zones where air is recirculated, there may be savings possible by using underutilized air from other spaces and bringing it into occupied spaces. So in that way, we can see CO2 savings. Generally, for most buildings, we're looking at reducing the ventilation-related costs of heating and cooling by anywhere from 10 to 40% in most buildings. The important thing to note when we're talking about outside air too is that, if you think about heating and cooling a building, recirculated air, as it comes back, you're only cooling it or heating it a couple of degrees to bring it back into a rational level for the space. But outside air, as it comes in and goes through the air handler, the temperature difference, the humidity difference may be quite significant. And so generally the amount of energy that you're spending on conditioning outside air far eclipses that of just reconditioning recirculated air. Now, one of the problems that's occurred and has made many buildings overventilated is a rule of thumb that we use in the industry that 20% of the air that comes into a building, 20% of the total air circulated within a building or air handler should be outside air. The problem is that if you set a damper position to about a 20% position, as this graph shows that was developed by the Portland Energy Conservation Center, down at the bottom of this graph is the position of the damper, and the y-axis here shows the percent flow. If we have a 20% open position, depending upon the pressure of the system, we will actually have potentially much more ventilation coming in. And this red box here shows the typical range of system pressures that we see in most cases. And you can see that a 20% open position brings in 40 to 60% outside air. That puts a great burden on the energy costs of the building, and actually in many cases means perhaps in very cold times or very hot, humid times, it may be difficult to control comfort in the building. So the key here is to have some sort of measurable feedback like CO2 that allows you to bring in just the right amount of fresh air. Now, we have a number of different solutions for measuring CO2, and that includes devices that can be used for wall mount, duct mount, in-unit mounting. We also have different ways that the sensors can be integrated into the building control system, including analog, LawnWorks, and BACnet. And also we have not just CO2 standalone, but also CO2 temperature and humidity sensors. And all units are self-calibrating. As you can see on the illustration here, we actually segregate the types of sensors into sensors that use a background ambient air self-calibration and other units that use a dual beam internal reference calibration. And I won't go into the details of the two here, but you can certainly contact us and we can provide you more information on that. Now, the biggest drawback that we've seen is with wired sensors, which are used in most new buildings today. When we get to retrofitting a building, Often the cost of installing wiring after the fact is very expensive. In fact, it can be $1,000 to $3,000 per point. And as a result, just a few months ago, we actually introduced the very first family of wireless sensors, including the absolutely first wireless CO2 sensor. And all these products are available now, and they include a CO2 and temperature sensor, a temperature and dew point or temperature and relative humidity sensor, um, a sensor that can actually take an analog output from any other sensor and turn it into a Wi-Fi signal, and finally basically a transmitter that has remote temperature probes that can be used to monitor temperature in a variety of places and broadcast that information to a local Wi-Fi network. All these sensors have a few things in common, including an ability to operate for 3 years on two AA batteries. They also, by the way, can be line powered so that you don't have to change the batteries. We feel that in many cases, you can save $700 to $3,000 per sensor by eliminating wires and using this Wi-Fi technology. And as I will talk about in a moment, it's very easy and inexpensive to integrate the wireless signal from the sensors into the wired control system of the building. There's also a way that you can take the information and actually send it to a AirTest hosted website where you can graph data and actually even have programmed alarms. Also, I should note that while Wi-Fi is our first entry into this market, we are later this year in 2014 going to be offering basically these same platforms, but they will communicate via the Zigbee wireless protocol. Now, there are a number of reasons why we've decided to do Wi-Fi first. First of all, Wi-Fi is everywhere. You probably have it in your home. You have it in your office. They're actually building it into cars now. And it's very widespread use. It's very dependable. I think we've seen that because of the size of this market, and it's growing all the time, the costs of using this are very low. Everything is approaching commodity pricing. And the other thing we know is that most people know how to log into a Wi-Fi network. They know how to troubleshoot a Wi-Fi network. If you're over 9 years old, you can probably set up a Wi-Fi router, or a number of people can. The other thing that's, I think, attractive about the Wi-Fi is that it's already got a vigorous security infrastructure intact. And so you can use the various security and encryption options that are already available for computers and other networks and really apply them to the sensors that we provide. The other thing about Wi-Fi is there's all kinds of ways that you can send data. Once you're connected to the internet, you can almost send it anywhere. You can send it to a web page. There are SQL databases out there that can take the information. There's IP, meaning Internet Protocol-based building control systems, and online gateways that can take the information and get it directly into the control mechanism of a building. Also, in some cases, even if you're in a building that has an existing Wi-Fi network, you may have an IT manager that's reluctant to have somebody log into that network. And the nice thing about Wi-Fi is it's very easy to overlay another Wi-Fi network working on different channels that can actually be used for the building control system, and in fact uses a totally separate connection, like a cellular internet connection to the system that's totally separate from whatever may be the enterprise system in the building. And of course, while we say Wi-Fi is first, we are looking at introducing Zigbee and a couple of other wireless protocols here as we proceed over the next 6 months or so. Just want to talk about with Wi-Fi then, there are really three basic options for sending data. One is you can actually send data from the sensor, have it go to an AirTest hosted website that actually holds the data and graphs it. It's accessible via any kind of smartphone, tablet, or computer. And it has the ability, if you want to set alarm levels, to actually send email and text alerts on alarms. You can actually track the progress on alarm response and so on. For this, there's a simple monthly fee per sensor that's involved. Also, we can provide a Wi-Fi to wire gateway, which is really shown in the lower illustration here, which will actually just hook up. You have a little device called the Babel Buster, which is connected to the Wi-Fi network and then plugged into your building control system. And all the building control system sees is the Wi-Fi sensor points as BACnet or Modbus objects in the wire system. Very cost-effective way of integrating into a system that already has a wired control system in place. And then if you want to send the data to any online controller, database, or web monitoring service, basically all you need to do is to be able to translate the information sent from the Wi-Fi sensors to the system you're using. And that involves writing a simple decompression app that translates the Wi-Fi data to usable data in the control system. We can provide the information on how to do that, and anybody who does programming of these types of devices on a regular basis should easily be able to write that application. So that's the kind of products that we have available for CO2 sensors. Now I'd just like to talk about some of our experience with having CO2 sensors and retrofitting them in stores. Obviously, stores are a great application for CO2 because they're designed for very high density, but the actual occupancy may vary greatly over the course of the operating period. So there's a great opportunity to save a lot of energy by modulating ventilation based on the number of people in the space. For about 5 years now, for example, we've been working with a large Canadian national shopper drugstore chain called Shoppers Drug Marts, where in initial testing we were actually save about 18% of the energy per store. Since that first test, we've now retrofitted almost 1,200 stores. And what they're seeing is by putting about 5 sensors per store in here, they're seeing energy paybacks of less than 2 years. And actually, we're now seeing many of the electrical utilities and even the gas utilities that serve the different areas where the stores are in. They're paying significant rebates to allow these sensors to go in because of the savings. This is another example in Canada where our CO2 sensors have been installed in 65 stores in Ontario, Canada. And here the gas company was very interested in the kind of savings that they could get in the wintertime. And you can see that they saved last year, I believe, over $240,000 in savings. And over 1 year, the cost of installing the sensors in those 65 stores was probably about half that cost. We've also worked with Lowe's in the US who have so far retrofitted about 600 stores with 5 or 6 sensors per store. They're generally seeing ventilation costs reduced by 30 to 50%. And, if you've been into a Lowe's at the various times of the day, sometimes it's jam-packed, sometimes there's hardly anybody there. So it's an ideal application for demand control ventilation. We've also provided sensors to most of the IKEA stores in the United States, where basically as part of a program where they wanted to be a silver LEED certified, they installed CO2 sensors but integrated into their air handling systems. And basically they were able to see ventilation cost reductions of 30 to 50% in those applications. In California, where I'm based, AirTest CO2 sensors have been installed in Ross stores throughout California. And then actually anything like a store that has design density greater than about 25 people per 1,000 square feet, the building code actually requires CO2 sensors be installed. And the reason for this is they did the calculations, and the energy savings for using CO2 in this kind of application is such a no-brainer that they decided to make it part of the California Energy Code or Building Code. Also, an ideal application for CO2 is actually in Southern California, where we have provided sensors to retrofit pretty much all the theaters in Southern California. This is one of the larger chains, Cinemark, and we've actually done a number of others as well. There are significant rebates available from Southern California Edison and from the California Energy Commission that made this all possible. So this really winds up the CO2 part of the presentation, but I guess the points to take away here are that CO2 demand control ventilation is really applicable to all buildings, that it's a viable way to control air intakes that typically have had no feedback or control. They've been set and forgotten, or in many cases, building owners may try and intuitively adjust them, trying to figure out what the right setting is. Inevitably, as indicated by the EPA study that I mentioned of 100 buildings, often the tendency is for people to set that damper too high, like at the 20% open position, and overventilate their building. So, um, and I think the thing we've learned and where the greatest implementation has been so far is in buildings that have medium to high densities, and that includes places like theaters, hospitality venues, excuse me, retail stores, shopping centers, schools, universities, and I think we also see, though, that uh, there's big savings in those applications, but also anywhere where green building, sustainable building criteria is being applied, people are putting in CO2 sensors because they want to know what the ventilation rates are in the building. And there's still savings to be had, they just may not be as high. So even applications like office buildings are a good candidate for CO2 demand control ventilation because you can actually determine space by space how much fresh air is actually getting to those spaces. I should also mention, and I'll talk about it a bit later in this presentation, that we do have an energy analysis program that can be used to estimate savings. Basically, the program looks at local climatic data, hourly temperature and dew point data over the course of a year, averaged over time. This is data that's used for doing building energy simulations all the time. And you can use this to really determine what the potential savings are for a particular building. This software, if you go to our webpage and go to the support section, you'll see a button to click on there that says energy analysis, and you can download a copy of our Excel-based energy analysis program. And so I think the other point here is that if you have existing buildings you're working on, you should consider the wireless CO2 and other wireless sensors because it offers a highly cost-effective way of doing retrofit. And one thing to note on the wireless side of it is a recent study by a major market research firm of building controls suggests that in next year, in 2015, about 25% of the sensors installed in buildings will be wireless. So this is a growing trend, and I think the big driver here, it's much more cost effective and just as reliable. Okay, so that takes care of the CO2 portion of the talk, and hopefully you found that informative. This next part is going to talk more about moisture considerations in buildings. And there are two sources of moisture in buildings, and that's really people, but by far, depending upon the climate you're in, the other source is actually outside air brought into the building, particularly when it's operated on the Economizer cycle. Now, just to give you a bit of background, we should understand what's happening in buildings today and how that affects some of our control strategies with regard to moisture. I don't know whether you're familiar with the term sensible heat ratio, but this is a rating of air conditioning equipment that speaks about the ability of the equipment to cool the air by lowering the temperature versus its ability to provide latent cooling or dehumidification to reduce the moisture. So the sensible heat ratio is a ratio of sensible cooling to total cooling capacity. And actually, most equipment today that's sold probably falls within a 0.8 to 9 ratio of sensible heat ratio. That means that generally 80 to 90% of the energy that operates a air conditioner, air handler goes into cooling the air, and only 10 to 20% of the energy actually goes into dehumidifying the air. And what we're finding here is because of changes in buildings, the old assumption that if we control temperature, we can control humidity is changing, and there are a number of reasons for that. Basically, over the past 20, 30 years, we've had lots of activities in buildings towards energy conservation that have included doing lighting retrofits, windows, window films, lower energy appliances, uh, higher thermal performance of walls, more insulation in walls and ceilings, and putting in setback controls. But all these measures and more that I haven't even mentioned all reduce the temperature load in buildings. So we're actually not having to cool as much anymore, yet the moisture load coming into the building is all the same. And what that means is we can no longer assume that controlling temperature in buildings also controls humidity, that some of the problems that we're starting to read about over the past 10 years or so related to moisture, mold and mildew, and so on, we're seeing in buildings is a direct result of the fact that temperature control no longer necessarily means humidity control. And this is further complicated by a few issues. A study done in 2003 by ASHRAE found that if an air conditioning system runs for less than 15 minutes, and that might happen if the building is under moderate temperature conditions or if the air conditioning equipment is oversized, if it runs for less than 15 minutes, water has no time to run off the coils. When the coil's off, air is still going through the coil, it's re-evaporated back into the space, and the net result is that no moisture is removed from the oil, from the air, and basically the moisture removal capability of the coil is nullified. So basically, we have a problem now that we may not be taking care of moisture in buildings as we take care of temperature. And in dealing with that moisture problem, if we can measure it properly, there are plenty of ways that we can deal with it. And that includes, one thing we've just talked about is using CO2 control to control the amount of outside air that comes in, which is a major source of moisture, so that we're only bringing in as much air as we need for the occupancy in the space. There's also possibility of putting latent recovery on outside air intakes, which include energy wheels or enthalpy wheels. You can actually buy equipment. Many equipment now, air handling equipment, does have the ability to vary the amount of cooling capacity with the amount of dehumidification capacity. And one of the things that's also useful, particularly in humid climates in the summertime, is to eliminate setback schedules when you know that it's highly humid outside and that humid air can infiltrate into the building, and then you have to try and dehumidify it all at once in the morning. The key here to all of this is you've got to measure and control the right thing, which in our viewpoint is dew point. So when we then take a look at this chart that I showed earlier, we've talked about the CO2 component, excuse me, but now we're going to talk about the economizer component. And let's just go on. Now, you may not be too familiar with what the fresh air economizer is, or you may be very familiar. Let me just provide a simple example here. This is a diagram of a typical rooftop air handler, where it draws air on the left-hand side from the space below. It's mixed with outside air, goes through a fan, and then goes through a heating or cooling coil that then the air is delivered to the space. You can see a damper assembly there that in normal operation, outside air is brought in, mixed with the return air at a 20 to 80% value, and then goes through the system. Well, when we do an economizer control, what happens is we have a sensor outside that senses that we have a sensor outside that's measuring conditions, and we have a call for cooling inside. Oh, well, let me just, again, this shows the proportion of airflow during normal operation. Then if we take a look at economizer operation, what we're doing is we're taking air through the return air and actually forcing it outside and bringing in 100% outside air, with the assumption that the outside air, let's say in the morning or on that particular day, is cool enough and dry enough that we can use that to cool the building rather than using the mechanical cooling in the space. And so the principal amount of air comes from outside, and this is what an economizer operation does. Now, there are a couple of options in terms of controlling the economizer. In many places in the US, economizers aren't feasible, but Roughly, they are installed on about 60% of the equipment throughout North America, actually. Uh, you can have economizers that decide to bring in outside air for free cooling based on temperature, based on enthalpy, which I'll talk a little bit more in a minute as to what that is, or based on, and this is something we're starting to champion, dew point and temperature. So let's just go through the different ways of measuring. Now, for economizer control, percent RH, which I haven't talked about, is really the ability for air to hold moisture at a different temperature. One of the problems with using RH as a control is that for every degree in temperature that you have a change, it actually affects the relative humidity of the air by 2%. So if you try and measure with RH, it's always a moving target depending on what the temperature is. Um, Often temperature is used, and temperature really, dry bulb temperature is the amount of sensible energy in the air. That's what the technical term for it is. And then enthalpy is really the measure of both the sensible energy, dry bulb temperature, and latent, which is really the energy that holds moisture in the air. Um, Enthalpy is a very useful measurement and calculation tool when you're taking air through a phase change, where, for example, outside air is coming in, going through a cooling coil, being cooled down, and you're condensing out moisture. The issue is that it's not really appropriate for the passive cooling approach that we use in economizer control, and I'll talk about that a little bit later. Finally, we have dew point and temperature control, and dew point is a measure of only the latent energy. So when we measure temperature, we measure the outside sensible outside temperature, which is sensible, and with the dew point, we measure the latent energy. So in terms of suitability then, percent RH really isn't applicable because of this temperature dependence I measured. Temperature is okay, but it ignores the moisture content of air. Temperature is often used as the default way of controlling an economizer because it's dependable. Enthalpy, being a total measure of the sensible and latent, could be useful, but it doesn't. There's no way to break out how much is sensible and how much is latent. So there are many cases, if you're using this as a control, you could be bringing in excessive moisture where the balance is really on the moisture side and not on the sensible side. One of the other issues about enthalpy sensors is there have been a number of independent studies that have questioned their accuracy and durability concerns. In fact, even if you take a look at the data sheets for most enthalpy sensors, you will see that they don't even state the accuracy of the sensor. That's not true of virtually any other sensor that you might put in a building. For dew point and temperature, the key to using dew point and temperature in economizer control is you only allow the economizer to bring in outside air when outside air conditions are below indoor design conditions. Indoor design conditions really define the temperature and humidity that is the upper limit that you will tolerate in the space. And every engineer, when he designs a space, establishes the indoor design conditions. Um, if you want a bit more background on the problems with economizer control, this is an article that appeared in the ASHRAE Journal in November of 2010 talking about why enthalpy economizers don't work. And one of the biggest reasons, and this study actually cites one of those independent reports, shows the testing data for one relative humidity sensor used in an enthalpy sensor. The two lines going across the middle of this chart are a plus or minus 3% range, which was the spec of the sensor, and all the dots you see on this graph was the actual performance of the sensor. So you've got to be aware that, and actually I think we see that people will install enthalpy sensors and then actually out of frustration, being on their rooftop and seeing that some dampers are open and some are closed on exactly the same day under the same conditions, people default to the temperature control. And when they do that, they're only controlling on sensible, and they're actually bringing in outside air when moisture levels are potentially higher. And actually, this issue is so significant that there's a humidity controlled design guide that was developed by ASHRAE. And in that guide, they really stated that traditional enthalpy economizers can bring in a huge amount of moisture by accident when temperatures are low but moisture levels are high. And air with a low enthalpy can carry a higher moisture content than what is desirable in the space, meaning really over design conditions. This can happen for thousands of hours each year during the evening, night, and morning hours when outside temperatures are low but moisture remains high. So there's a problem. And really, out of that problem, there's a simple rule for economizer control, and that is that an economizer strategy should never allow incoming outdoor air to exceed the indoor design conditions for moisture or temperature in the space. So what are those indoor design conditions? Well, if we take a look here, a couple of typical indoor design conditions. Basically, they're often stated at a certain percentage at indoor design temperature, probably in most cases 50% RH at 72 degrees is the indoor design condition. But if we want to understand what does that mean in terms of how much moisture I should allow in my building, then we really have to translate that to a dew point measurement, which is indicated by the T small d. And you can see here that 50% RH at 72 degrees results in a 52.5 degree dew point level. The other interesting thing about using dew point, of course, is it can actually help us predict when condensation might occur in the building. So 52.5 degrees means that if you have a nice cold glass that's 52.5 or below, you're actually going to see condensation on that glass. So what's the implication of actually using these three different strategies? This shows a number of cities in the United States and the number of hours that the economizer operates when it's using enthalpy. And in this case, we're assuming an accurate enthalpy sensor that actually lasts on temperature and by dew point and temperature. And you can see the conditions for enthalpy. We're calculating at 29 BTU per pound. For temperature, we're looking at 68 degrees. And for dew point temperature, we're looking at that 52.5 degree F dew point and 68 degrees, which is equal to 50% RH at 72 degrees. Now, this data, this simulation was taken from AirTest energy analysis program that looks at the hourly temperature and dew point data in the space and is typically used for weather energy calculations. So the dark blue bar here shows the dew point and temperature. This is showing the actual number of hours that the outside air is suitable for or is below the indoor design conditions. The light blue line and the red line are the enthalpy and temperature only, and anything that goes past the blue line is actually indicating where those economizer control strategies are bringing in moisture over and above indoor conditions. And you can see that for many cities, it's a significant period of time. So what's happening here? A lot of moisture is being brought in from outside. That moisture is being absorbed into the walls, the ceilings, the furniture of the building. And when the air conditioner comes on, part of its task is not just to cool the air, but it's now to bring this moisture out of the building and get it back to design conditions. So really, these times that these systems operate above indoor design conditions are really times when it's not appropriate they should be operating, that you're really not saving energy when you're doing this. The other thing to note is, of course, when an economizer is operating, CO2 control does not work. And so that also these hours, outlined by the yellow box, are hours where you're losing savings from CO2 demand control ventilation. You have marginal savings from economizer, if any, or maybe negative savings, and you're not reaping savings from CO2 control. So this is one of the reasons why we see the use of dew point and temperature as being an important economizer control strategy. If we look at our friends in Canada, this basically shows actually in Canada, they have a much more of an issue here. In some cases, like Montreal, it's almost 2/3 of the time that a normal economizer might be operating, they're bringing in moisture levels way over indoor conditions. I might also add, the conditions we're looking at here are conditions that would be typical for a office space or something like that. If we're starting to talk about retail space that has coolers and freezers and so on in it, your dew point level really has to be a lot lower to ensure that you don't have condensation and fogging on freezers. So the impact of really the temperature enthalpy approach is that they can introduce unwanted moisture in the buildings. That moisture is absorbed by the building materials, taken out later when the AC is active. Energy has to be used for this dehumidification, and the economizer benefit is really null for hundreds or in some cases thousands of hours each year when CO2 DCV could be delivering significant energy savings. The negative impacts will be significantly greater, as I mentioned, for areas that require low dew point conditions like retail stores that have food storage in it. Also, the other area that's of concern is buildings using chilled beam or radiant cooling type applications. So the AirTest approach for dew point control is to have a sensor that actually sits outside and measures outside dew point conditions. The sensor we use is durable. It's a weather station quality temperature and humidity sensor with excellent long-term stability in outdoor environments. It means it can stand up to salt, air pollution, condensation, and so on. And it's designed to go 10 years without calibration or any kind of maintenance. We also put over it a radiation shield that protects the sensors against the elements and ensures that you're making an accurate measurement and that's not affected by wind, rain, snow, or solar radiation. Often outside sensors are placed outside and they're not properly protected, and their accuracy just goes out the window because it's not properly protected. Finally, with the output from the sensor, you can either calculate dew point in the probe. We have probes that do that, or you can provide the temperature and humidity information that allows the building control system to do the calculation. The important thing to note is you can put one of these devices on the outside air and it can be used to control all the building air intakes in the building. For us, we have three different product options. One that provides a temperature and humidity output, 0 to 10 volt. Another one that provides a Modbus output, where the dew point is calculated, temperature is calculated. And a third option, which actually will provide you with an analog output of dew point and temperature, or even if you still want to measure enthalpy, it will give you an enthalpy calculated measurement. We also have, as I mentioned earlier, the Wi-Fi analog module that allows you to take an input and put it into a Wi-Fi system. In this case, we actually attach the radiation shield and the humidity sensor directly to this device, which is mounted inside the building, and we can then use that as part of the overall signals back through the Wi-Fi system to the building control system. Now, just to talk about a couple of examples of that, we've been working with one large telecom that has installed our sensors in about 13,000 of their cellular equipment buildings. They have one outside dew point sensor, dew point temperature sensor, and one inside. And basically what they do is they only do free cooling with these sensors when the dew point is below the target level. And based on 4 months of installation, they're already saving hundreds of dollars on every installation. In fact, we have others currently evaluating this product and looking at a 3-month period from February to April, they reduced their operation from 24 hours a day to 5 hours a day by effectively using free cooling. Of course, a key aspect of these cellular stations is many of them are in isolated areas, and they wanted a sensor that they knew would last for as long as that cellular station would. They don't need to be sending somebody out to change out an HVAC grade sensor when it goes wrong. The cost of getting somebody on a helicopter or a truck to drive out to where that is would be prohibitive. So they've chosen to take these sensors and which are more accurate and durable. And quite frankly, though, with this kind of volume we're now seeing, we can make the prices quite attractive for this type of sensor. A second example I want to talk about is the city of Pasadena, which is located in a part of California really considered dry, where moisture isn't an issue. But in the morning, the moisture levels can be high, and that moisture coming in the building can affect comfort. So basically, what they decided to do was take one dew point temperature sensor and use it to control all city buildings within about a 10-block area. And this is an aerial photo showing where City Hall is, and there are numerous city buildings within that 10-block area. Basically, in doing this, they realized that the best comfort conditions occurred by maintaining indoor dew point sensor or the economizers to provide a 51-degree dew point limit. So, and basically, the building operator there started at 55 and just played around, and where the best comfort level came in, that's what he chose to do his ongoing control with. And of course, all these buildings have CO2 demand control ventilation, and by using the dew point, they're maximizing the hours where CO2 control can be used. I might also add we offer a CO2 energy analysis program that actually does look at both potential savings from CO2 and from actually economizer control. And this shows the Canadian version of it, but basically we have selections for about 270 locations throughout North America. You can basically pick the location, put in some parameters of the building. As I mentioned earlier, we use local hourly weather data, energy costs, and estimated occupancy to estimate CO2 savings. This, as I say, also will allow you to estimate the use of CO2 control with various economizer control strategies, which include temperature, enthalpy, and dew point and temperature. And this just kind of gives an idea of what the savings results look like, where we have a base case cost, assuming the building is operated continuously. We estimate heating and cooling costs, and we take a look at the same thing using the CO2, and we can calculate then what the CO2 savings are, including the greenhouse gas reduction. And then we also have basically an analysis that says, well, let's look at the savings from CO2 and the savings from Economizer, add them up to see which gives us the total best savings. And of course, again, with enthalpy or some of these approaches, you're cutting out the number of hours the CO2 sensor can save and delivering marginal savings. So in this example, if you take a look at the savings that are provided by the different approaches under total savings, you can see by far the dew point and temperature economizer control with the CO2 control provides $871 worth of savings, which is far beyond any of the other options. So the total optimization of building ventilation for economizer control and temperature control best occurs with the dew point temperature economizer control combined with CO2. So to summarize on this, CO2 demand control ventilation can be used in buildings to modulate outside air based on actual occupancy, and dew point economizer control can provide free cooling only when it's appropriate to maximize CO2 savings. Also, we didn't talk about it, but there are good reasons to measure indoor dew point for nighttime setback control or dehumidification control in the building. Also, obviously, measuring temperature, particularly using some of the techniques that we've described here earlier, could be useful in those same buildings. And I've told you a little bit about our wireless, which can reduce installation cost and increase payback. And really, that's our presentation for today. I might suggest that here's some links for some more information. You might just want to pause this video for a minute and write down the links. And from there, particularly the third link down, will have reference to a number of product and white paper information that you can go to get more information. Of course, you can go directly to our website as well. Thanks for spending the time here, and if you have any questions, you can contact me or AirTest directly. Thank you very much. Have a good day.